Welcome back to another short video. This time we are going to solve problem 58, spiral primes from Project Euler. So let's see what the problem is about. Starting with 1 and spirally anti-clockwise in the following way, a square spiral with side length 7 is formed. So if we anti-clockwise perform a spiral around the first cell, which is 1, we are going to perform this operation repeatedly, and it is interesting to note that the odd squares lie along the bottom right diagonal. As you can see, this diagonal contains all the odd squares, but what is more interesting is that 8 out of the 13 numbers lying along the both diagonals are prime. So we need to essentially count the number of primes along both of the diagonals and check how many of them are prime. And they are saying that for this side length equals to 7, the ratio of primes along the diagonals is 8 by 13, and if one complete new layer is wrapped around the spiral above, spiral length with side length 9 will be formed. So as you can see, performing one spiral operation is increasing the number of rows and columns by 2, and it is always odd. So this is one of the observation, and they are asking us to find out if the process is continued, what is the side length of the square spiral for which the ratio of primes along both diagonals first falls below 10%. So we need to keep adding those layers one by one, and when the ratio of primes along the diagonals falls below 10%, we need to report what is the side length when the first time it falls below 10%. So let's see what the question is about. So first of all, if we index the grid from left to right for the columns and from top to bottom for the rows, for side length equals to 3, we have this grid, and this two cross lines represent the main and the secondary diagonals. So if this green one is the starting cell, and this orange one is going to denote the iteration, which is going to add a surrounding values to all the cells in the current cell. If we add one more layer to this, the innermost grid remains intact, and a new layer is added, which is denoted by purple color in this one. So as you can see, the ending position of the previous iteration was 9, and from there only we continued. So here we started from 1, we went to the right, and in the anti-clockwise direction we finished at 9. So here also we are going to start at 9 and perform the anti-clockwise spiral of adding layers, and this process goes on, and we need to find out for which side length the ratio of the primes along these two diagonals fall below 10%. So this is the question in brief. So if we had to simulate this, let's see what is the process. First of all, if you observe that if we start with the unit cell, which is 1, we are essentially going 1 unit to the right, then going above as much as possible, then to the left as much as possible, then to the down as much as possible, and after that to the right as much as possible. This way we are going to add a layer to the innermost grid in each iteration. So 1 will be the starting position of our iteration, and this brown cell is going to be the ending position of the iteration. For the next iteration, we are going to start where we left, or where we ended our previous iteration on, which was this cell. This was containing 9. Now if we start again, repeat the same process, one step to the right, and up, left, down and right, we are going to arrive at another ending position for this iteration. So if you observe that, the main pattern you can observe is, first of all, we are going to step one step to the right from the ending position of the previous iteration, then keep going up until the boundary is reached. So as you can see, previously the boundary for this iteration was that this grid is going to contain 3 by 3 rows and columns. For this it was 5 by 5. That's why for this cell to go up, it had a limit of going 3 steps up. So each iteration, the side length is also incremented by 2. As we saw, adding a layer is going to increment the number of sides by 2. So initially it was 3, adding one more layer made it 5. So this is the observation. So after this, we are going to check what is the pattern. The pattern was to go one step to the right, then up as much as possible, left, down and right respectively. And we are going to arrive at that iteration's ending position. So as you can see, this is the illustration for that pattern. We start with the cell of previous iterations ending point, and we simulate the process of going one step right, up, left and down and then right, and the ending position of this iteration will be used for the next iteration. So let's see what all information we need to keep track of to know the number of primes and what is the current cell that we are at, and to essentially perform the entire simulation one after the other. So first of all, we need to know what is the coordinate of the current cell, Cx, Cy, then value in that cell. So if we are going to move from one cell to the other, we are essentially incrementing the value by 1 because we are stepping 1 ahead of the current cell, and the values are sequentially ordered, hence the value will be incremented by 1 in each movement. Then R1 and R2 denote the upper and lower limits for the row number, and C1 and C2 the left and right limits for the column number. So here it should be column number. So let's also see what that denotes. So essentially we are going to start at Cx, which was the ending point of previous iteration, simulate the same process, and we need to also know what are the boundaries until which we can perform this 4 directional movements. So essentially we are bounded by R1 and R2 for the row numbers and C1 and C2 for the column numbers, and the Cx, and value are the position of cell that we are currently at and what is the value in that cell. And we also need to know what are the count of prime numbers in the diagonals of each iteration. So once we add a layer, while adding the layer itself, we are going to increment the number of counts if we found that the cell is currently on any diagonal. So let's also see how we are going to check whether the cell that we are currently at is a diagonal or not. So after each movement, we are going to update the count of primes in the diagonals. So how do we check whether this current cell belongs to the diagonal? So as you can see from this we saw earlier, this is the main diagonal, top left to the bottom right. As you can see, all the cells in this diagonal are going to have the same x and y coordinates. So 4, 4, 3, 3, 2, 2, 1, 1 and again 0, 0. So that is the main observation for the main diagonal. For the secondary diagonal, you can see that the sum of coordinates is constant. So 2 plus 2 is 4, then 3 plus 1 is 4, then 4 plus 0 is 4. So for the secondary diagonal, the sum of coordinates Cx plus Cy will be 4. If we started at the first cell from 2, 2. So essentially the expression turns out to be that for the main diagonal, the Cx and Cy will be same. For the secondary diagonal, the sum of Cx and Cy is going to be twice the coordinate of the starting position, because we are wrapping one layer one after the other. Hence the coordinates of the first cell that we have considered is going to be added up each time, and the secondary diagonal will have the property that sum of coordinates is twice the starting coordinate. So let's also go through that once again. So for the main diagonal, Cx will be Cy, and for the secondary diagonal, Cx plus Cy is twice Cx, capital Cx, where capital Cx and Cy is the starting cell's coordinate. So we don't know whether we need to start this cell with value 1 at which position. It could be 100, 100 or 1000, 1000. So depending on that, the secondary diagonal will have the property that Cx plus Cy is twice the coordinate of the starting position. And This process needs to be simulated through an infinite loop because we don't know where to stop. The point at which we need to stop is the position for the answer. Hence, we need to simulate it one after the other. So let's also go through the implementation now. So I have created a max variable to store the prime numbers for all the numbers in this range. Then I've also used a square root function to prime check the numbers if it does not belong in this range. So this is 5 into 10 raised to 7. If the number goes beyond that, we have not computed it, and we are going to check it using this square root algorithm. This is the sieve algorithm, which is going to pre-compute all primes up to the value max. Then we have the starting position, which was cx and cy, capital Cx and cy, that we denoted earlier, and this was the bounded r1 and r2 values. So this r1, r2 and c2, I have initialized them with 100, 100 initially. Then this is going to denote the number of primes in the diagonal, the ratio that we need to check. This is going to return whether our current cx and cy coordinates are inside our grid boundaries. This process is 1 unit of movement. So if I'm moving to the next cell, I'm going to increment my value, and also this condition is for checking whether the current cell is the diagonal cell or not. So this is for the main diagonal, this is for the second diagonal. Again, this is twice the coordinate of the original cell, and if this value is less than equals to max, I'm going to check prime using sieve pre-computed values, or if it is larger, I'm going to run this algorithm for checking prime, and it will be incremented if it is a diagonal. So this is the process of 1 unit of movement for each cell, and this is the iteration for each cell. So this process is going to start at the first cell, hence it is called initially. Then this is for logging purposes, to know at what iteration we are currently at. For stepping one step to the right, we are incrementing the y coordinate, and each iteration is going to extend the boundaries of the rows and the columns. So the uppermost row will go one step up, and the lowermost row will go one step down. Similarly for the column boundaries. Then there are some assertions for checking whether the current cell is inside the boundaries. Then again, we performed one step movement, hence we are also going to account this for a movement while checking the diagonal prime count. And this direction is going to iterate in the directions that we mentioned in the diagrams. So essentially, the first movement was to go to the upper direction, which is -1, 0. If you look at the dx and dy arrays, so essentially this is the first index of these two arrays is going to denote where the direction of the current movement is going to go. So if you're going up, the x coordinate decreases. If you're going left, the y coordinate decreases. If you're going down, then x coordinate increases. If you're going to the right, the y coordinate increases. So this is the order in which the directional movements are going to happen, and we are going to perform them sequentially in the 4 directions. And as long as the point lies inside the grid boundaries, we are going to update their coordinates and process them and add it to the answer. So after this entire process is completed of going through all the 4 directions, then we are going to add we are going to update our ratio, which is checking the ratio of diagonal prime count in the current grid. So if that is less than 10%, we are going to print our answer. And the denominator is going to be the number of elements in the diagonal, which is simply twice the side length -1, because the center element will be counted twice. So this will be the denominator, and the numerator will be this one, and that ratio should be less than 1/10. Hence I've shifted the 10 term to the left side and used this expression for checking. So this will print out the answer for us. So Yeah, that was it about this video. This was a short one. It was fairly simple problem, but the implementation could have been difficult depending on your ideas and thoughts. So do let me know if you have any optimized solution for this. And yeah, thank you.